Alright, so there was the little warning. Uh, on Thursday, I'm going to have a couple different data sets for us to go over. These will be things that you do or will actually analyze pretty much the entire time we're here. You will be writing your results up on the board, and then we will be looking at what everyone got. But before we get to that point, we should probably talk about why everyone's going to get completely different answers on Thursday. When if you read any particular uh like stats textbook or go talk with any stats professor, they're going to tell you no, 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 no. You get the same thing every time. And the answer is no, you don't. So, two things that I want to talk about. One of them is data preparation. A lot of times the data that you get is, especially in things like this, or if anyone does like Kaggle competitions and all that, the data is already set. You just plug it into your software or you upload it into your software, hit a couple of commands, and things happen. When we deal with data in reality, uh, unless you're really, really skilled with like SQL Server or SQL programming or stuff like that, the data is almost definitely going to need to be manipulated somehow. And when I say the data needs to be manipulated, I don't mean uh, deleting things because you don't like the result that it would give you if you left it in there type of thing. Just how do we go about dealing with this data in the first place? So when we're talking about ANOVA, we were discussing, suppose you're doing a clinical trial or looking at data from a clinical trial, and you've got essentially a control group, which gets the current, say, standard of care, another group that gets a standard of care plus, say, 1 unit of A, medication A, standard of care plus, say, 2 units of medication A, standard of care plus 1 unit of B, standard of care plus 2 units of B, and then standard of care plus 1 of A plus, say, 1 of B, something like that. When we were looking at the results with ANOVA, we're looking at the average of, say, this group and potentially trying to compare it against the average of all these other groups. We saw that when you start trying to compare every combination or every pair that you can make here, that creates a huge freaking mess. If I was to give you data like this, uh, and you run through and you do ANOVA, you will get results. Because of how I've got all of these things actually set up, getting back to data prep, if so, if I gave you all this data and for ANOVA analysis, you would have a column for standard of care, a column for standard of care plus 1A, then 2A, 1B, 2B, and so on. But that's only if we're going to be doing this in Minitab. For the students I'm teaching in public health, this because they're using a completely different software program from you guys, I actually have to do a 45-minute video on just how to take data from the way you're most likely going to see it, just so you can analyze it in SPSS, and then another 30-minute video to show them here are the buttons you click on to get the answers that you're looking for. So if my data is normally like that, and let's say uh, we can think of, say, 0 extra medication, 1 unit of A, 2 units of A, 0, 1, 2, 0 extra medication, 0, 1, 2, 0 units of extra medication, then 1 and 1. We can actually rewrite these as column. So I'm going to call this group A, B, C, D, E, and then F. I can take all this information. It's going to be a whole lot of copying and pasting, but I can actually create 2 new columns, call it Med A, Med B, and then we'll call it results. And this wouldn't necessarily be a column that I'd make, but just so we can show, or I can show you where all this stuff is actually coming from. Now, if I'm going to prep the data, so let's say I'm going to take everything from the standard of care, copy, paste it down here. So for everyone that's in group A, under medication A and medication B, I just type in zeros. When I get to medication B or group B, again, have to come back, copy, paste it. Since they're getting 1 unit of A and 0 units of B, I can do that. Group C, again, copy, paste into the results column. But group C gets 2 units of A and 0 units of B. For group D, again, copy, paste into results. So group D, they don't get any of medication A, but they get 1 unit of medication B. Copy, paste group E. We can again do 0 and 2. And then say with group F, since they get 1 unit of each, for everyone that's in group F in medication in A, medication B, type in 1 and 1. And then, of course, copy paste the results over. I'm not actually going to do that because this was already boring enough. And I figure you all know how to copy and paste things in Excel. If you don't, what class is it? ISM 120, something like that. Go back and retake that. Or go back and look at your notes on there. Nice thing is, when we analyze the data like this versus analyze the data as ANOVA, the ANOVA table is still going to look pretty much the same way that it was. But if you remember the ANOVA table, and again, this is part of the homework, this is going to be part of the second exam, this is going to be part of the final exam, what ends up happening? So if we're doing an ANOVA table, where we've got, say, model, and then error, and total, and we've got these degrees of freedom here, and then we've got, say, the sum of squares over here. And let's say, again, with our 6 groups, there were, say, 20 people in there. So n is going to equal 120 people. Degrees of freedom total here is going to be 119. If we're doing this ANOVA table with ANOVA, how many degrees of freedom do we get here? Well, it's the number of groups we have. So 6 minus 1. So we're going to have 5 up here and 114 in this group. If we go back And I don't know what say the sum of squares is going to be, but let's say the total is going to be about 2000 here, and let's say it's like 500 up here. As a reminder, you're going to have to figure out what goes in the middle there. So 2000 minus 500, 1500, something like that. If we try to fill out the same table using the linear regression, which is essentially what we're doing by reformatting the data and prepping the data, taking it from whatever we had over here, just making it into these two columns. We're still going to have the source. So there's still going to be something for the model. There's going to be something for the error. There's still going to be something for the total. Degrees of freedom and sum of squares will be a little bit different. It can still be, say, 2000 down here. The total we're going to have for degrees of freedom is still going to be 119. But the values that go into each one of those spaces is actually going to change. Potentially, anyway. So starting off with something like this, if we were to fit that full model, we would have results. So this is going to be whatever that y value is, whatever it is we're trying to model, whatever it is we're interested in looking at. We're going to still have the beta 0, beta 1, say medication A, plus beta 2, medication A. But because we've got 0, 1, and 2, we can actually add in a quadratic term here. I'll try to zoom in on this a little bit. So next would be, say, beta 3, med B, plus beta 4, med B squared, plus beta 5, med A times med B. Since in this case, we actually do have patients that are getting both of these medications at the same time, we can add in this thing over here, which is called an interaction term. With those interaction terms, if we're talking about medications, there's possibility that, say, medication A might actually interfere with medication B, making it so that if you take both of them, it's less effective than if you took one of them by itself. If you've ever watched any commercial where they're talking about, do not take this medication if you are on, and then they list a whole bunch of things, or say your parents or grandparents have certain medications, uh, and you look up those medications, there'll be things that you find on like WebMD, places like that. Do not take this medication along with, say, St. John's wort. Do not take it along with aspirin. Do not take it along with this, that, or the other, because it'll affect the way that the medication actually works. Sometimes this interaction will make it more effective, potentially too effective. So for example, if you're taking certain types of blood thinners, Blood thinners make it so that you bruise fairly easily. If you take aspirin, it's also a blood thinner. It makes it so you could bleed really easily. You take both at the same time, it's quite possible that you could die from a bloody nose because your blood just will not clot because it's just so thin from both of those medications. And if you if you're like, could you really die from a bloody nose? Try Googling it. There are a lot of people that actually have such severe bloody noses that they, even with emergency room help, they could still die from that. For those of you that say take aspirin and then look at, say, what is the difference between aspirin and extra strength aspirin? Anyone ever do that before? If you look at regular aspirin, it's usually like 325 milligrams of aspirin, which I believe is salicylic acid, just as it is. When you take the extra strength, it's usually a 10 to 1, I think it's 10 to 1 combination of caffeine plus aspirin. So if you take, say, 2 regular strength aspirin and then drink a cup of coffee, that's kind of the same thing as taking one, maybe 1.5 extra strength aspirin. And the reason they put the caffeine in the extra strength aspirin is because the caffeine by itself does not help with any pain relief, but it kind of supercharges the aspirin to make the aspirin a lot more effective. So sometimes these interactions can be really, really important and give you better results than you had thought. Sometimes uh, it, these interactions they work together and make things even worse. Uh, Several years ago, I was giving a presentation for the American Chemical Society at, I guess it's over that way, at the Henry. I went and collected some data. So I had a tasting panel. Everyone in the group is an adult over the age of 21. So we did beer tastings. And I did mixtures of different beers. Uh, at one of the breweries where I collected data at, we actually found that mixing two of the beers was a heck of a lot better than either one by itself. And then showing the owners and showing some of the beer professionals that were there, the results, they're looking at it saying, that doesn't make any sense. It shouldn't be like that. I'm like, well, have you tried it? Then they did. They're like, oh my God, you're right. This is a lot better. So it goes completely against their theory at the time. At another place, I actually uh, initially had the tasting. Has anyone ever done like a taste testing for anything? Usually they tell you on a scale of 1 to 10, 1, this is the worst thing you've ever tasted, 10, this is the best thing you've ever tasted. Where does this particular thing that you're tasting land? Uh, that was basically the scale. A mixture of two of the beers was so horrendous that we had to change the low end from this is the worst thing you've ever had to you end up retasting it fully. And we had some 1.5s, maybe 1.25s. So in that case, the interaction, the combination of those two beers was made it so much more horrible than either one by itself that we needed to have a garbage can near us for the rest of the tasting, just in case. So again, you look at what would be the theory behind it, why would it be that bad? There is no particular reason, it just happened to be that way. Uh, if you get into quality control, a lot of what you learn about in quality control from designing experiments to see how can we make this product with fewer defects, blah, blah, blah. a lot of times it's actually going to be these interactions here. One of the statisticians for whom I have a considerable amount of respect, he actually went into statistics from chemistry, kind of like I did, and he invented a lot of things. And he actually went into a chemical plant and tried to increase the purity of a certain product that they were making. So the goal here, so the results are percent yield or percent purity, however you want to look at it. According to everyone that had been working at the plant for the last 50 years, you turn things up when you need higher purity or if it's not working out that well. Well, he went in, did a small experimental, what's called an experimental design, and actually found that the 50 years of knowledge from everyone that had ever worked in that plant on those, or in that facility was actually the opposite of what they should be doing. So the experts were wrong and very, very wrong. And when they realized you had to actually turn two things down at the same time. And when you did that, the purity went through the roof, cost plummeted, and millions were saved. And this is back in the 60s. So by now, that company has now saved several $billions by not listening to their experts that have been working on the line and working with this particular system. So, and the big idea or the thing that really did it was being able to look at this interaction term here. So if I have the full model the way that I've got it now, the degrees of freedom that actually go up here is equal to 1, 2, 3, 4, 5. So it's going to be basically just like we had before. But as you saw with some of the stuff we were doing last time, there's a chance that some of these beta values here might not be statistically significant from 0. So if that's the case, the number of degrees of freedom that you put in here is going to be the number of terms that have, say, med A or med B in them. There might be 2, there might be 3. We might need all 5. We might need only 1, because we might actually find that med A is the only thing that really works, and med A is linear. We might find that, say, med A is the only thing that works, and it actually has like a quadratic effect. With these quadratic effects, if they're part of the model, then we'd have to put them in there. So let's say med A and med A squared were the only thing that were significant. Then where it says model, we put in 2. So the degrees of freedom over here are going to change. And we have to keep in mind with linear regression, the stuff that goes in for this model, that's going to be the number of leftover terms that we have in the model. For the data we're going to look at on Thursday, and probably every Thursday from now on, there are going to be 50, 100 different variables. And it's basically going to be your job to go through, analyze the data, and then report back the data, okay? So we're going to be using software for this, so you don't need to worry too much. But to keep in mind, when it comes time for these, you have to look at how many significant terms are there. That's what goes in here. The error here is still going to be, say, total minus the number that's in the model. If none of these beta values are statistically significant, then the results are just basically whatever this is, and that's essentially the average. So when we're dealing with the data prep, sometimes it's just boring, sometimes it's literally downright annoying. Just as an example, the some of the data I collected and presented to many higher ups at, say, Henry Ford College and also at Oakland Community College, showing how to improve student outcomes significantly and cheaply. Uh, had to go through, take the data set that I've got, use basically Microsoft Access, join the data in a certain way, eliminate the duplicates, eliminate so if a student goes from math class A to science class A, uh, make sure that they took the math class A first. Some of the data prep that I had to do for these presentations took 15 hours. The analysis in total, 10 seconds. But it was 15 hours to do 10 seconds of work. Dear God, that was horrible. If you're better at programming in SQL than I am, you can eliminate some of that, but instead of 15 hours of prep work, it probably would have been 10 hours of prep work because you have to keep going back, checking to make sure that you're getting all the data that you're supposed to, and you haven't eliminated valid data. Oh, so anyway, with what we're doing here, again, the ANOVA table that we're going to get, it's going to change. It's mostly going to change because of the degrees of freedom. And the degrees of freedom, when we're looking at the model, if you wanted to, you could look at it as the number of terms in the model minus one. So if there only happens to be, so if that happens, what you're seeing right there, if that happens to be the final model that you're dealing with, there's 1, 2, 3 terms. Degrees of freedom here is number of terms. So 3 minus 1, you plug in 2. And then you'd have sum of squares divided by 2 to give you your mean sum of squares and all that. The calculations for mean sum of squares is the same. It's just the numbers that go in here are going to change, which is going to change the values that we have over here, but it's still going to be the same type of process. This plus this has to equal to whatever this is. So it's something to watch out for. It's something that you need to deal with. So on to the other part. Uh, with the data that I'm going to give you, there's going to be somewhere between 10,000 to say 100,000 rows of data. So you're going to look on the side and it's going to start off at 1, you get all the way down to the bottom. You'll be in like row 10,001 or whatever it happens to be. Number of columns, could be 50 plus. If you're using real data, if you're trying to do these types of analyses for real, say for your company, you're going to be looking at all the data that they have, and then you're going to spend a considerable amount of time, or software is going to spend a considerable amount of time trying to figure out what seems to actually be important for predicting whatever this outcome happens to be. So when we're dealing with a large data set like this, compared to, say, a traditional stats class, this is going to be large data. But you know what? Every time someone, say, goes to Walmart and performs a transaction of some kind, how many transactions happen at all Walmarts all across the entire universe every single day? And we can think of each one of those transactions as being, say, a row. Some of the variables that you're going to get are going to be what? The dollar amount spent, uh, the time of day that it happened, the store that it happened at, and then each one of the columns could actually be, say, every single product they have in stock. How many different products does Walmart have in stock right now? Again, all across all of their stores everywhere. Yeah, hundreds of thousands, potentially millions. And what's going to end up happening, again, if we're doing this for real, you might have something about the store, you might have something about the store, the time of day, the amount that the was paid, and then for every product out there, everything's basically going to be set to zero unless you bought that product. Then you get a one. You bought two of them, you get a two. You had one of those 5 for 5 sales and you bought 10 of them, it's going to mark you down as 10. And then we can start using that data in that particular format to start doing all sorts of the different types of analyses, none of which we're going to do in here. But if you do take that data science class, uh, what is it, DS 325 or whatever, uh, they actually get into something called market or shopping basket analysis or shopping cart analysis, where they try to look at what are products that seem to be bought in combinations. And then if you know how the game is run or how the game is rigged, uh, just as an example, you go to the store, you buy peanut butter, you buy jelly. What are you making? Peanut butter jelly sandwiches. What else do you need to make a peanut butter jelly sandwich? Bread. So if you don't buy bread, more than likely you're going to get a coupon because they realize, hey, people tend to buy stuff from this peanut butter category or nut spread category, as well as the jelly and jam category. And they also tend to buy bread at the same time. So more than likely, the machine that you have is going to come up with, or the machine that you're at is going to print out a coupon for, say, 50 cents off a loaf of bread. Does it know if you have bread at home? Absolutely not. But it knows that, say, 95% of the time when someone buys something from the jelly category, something from the peanut butter category, they also buy bread, and you didn't buy bread, their best guess is you should probably be buying bread. You just forgot to grab it. So if you ever see that coupon for bread pop out and you're like, man, I forgot I'm supposed to get bread. They don't know. But because, like I said, 95% of people that buy peanut butter and jelly at the same time also buy bread, they're going to print out the coupon just as a reminder. Why? They want more of your money, right? When you have these systems set up properly and you're doing that type of analysis, it works out really well because you can prompt people. Just as an example, bought an auto part, and uh, with that auto part, it said customers also bought these 3 other auto parts which actually attached to it, so the hoses and all that. If you just bought the auto part by itself, great, it's going to fit, it's going to work, but you also need to replace all the hoses at the same time. Well, that wasn't on the box. That's not in the part. That's something that you figure out once you try to put that auto part on and then go, oh, I can't reuse this hose. Son of a. So sometimes it works out well. Sometimes though, and this is something that we're going to be dealing with a lot, pretty much every Thursday from here on out. Sometimes there's something called a spurious correlation. So these spurious correlations, uh, they just because of how data is, and like I said, we're going to see a lot of this pretty much every Thursday for the rest of the semester. A spurious correlation, when you perform your analysis, it's going to appear, at least to you, as though it is statistically significant. So it appears to be statistically significant. It appears that there might be something going on here. But it's wrong. It literally does not belong. And with the data set that I'm going to have for you on Thursday, we're going to be looking at it again, say 10,000 data points, 50 to 100 columns. I'm going to be creating the model. So I know what is important and what's not. And more than likely, what's going to happen is with every single one of you, when you do these analyses, you're going to get a bunch of these spurious correlations. And you're going to know straight up it does not belong. And you're going to know that it does not belong because I'm going to tell you what's in the model and what is not part of the model. But we're going to pretend like we don't know that. Because when you're looking at real data, you actually don't know what has an impact on the outcome. There might be theories, there might be thoughts, there might be hopes and dreams that the stuff that you can easily collect will actually be valuable and viable for whatever it is you're dealing with, but there are no guarantees. So part of what we're going to be doing is trying to figure out how can we say perform the analyses that we're supposed to and hopefully eliminate as many of these spurious correlations as we can. And then once we've done that, uh, and I know that a lot of you are probably already going to be way bored with it, but when you look at the results over and over and over and over again, what we're actually going to find is that sometimes the things that belong in the model will not be there. Sometimes things that don't belong in the model will be in there. And with these various correlations, depending on what it is, like let's say, for example, you're working as a working in the finance department or the accounting department at a hospital, and you find that people with certain conditions seem to get $50,000, $100,000 MRIs all the time. Well, why do they get that? There have actually been some studies dealing with Medicare and Medicaid where that sort of thing happened. Statisticians went back, looked at all the information for people that had, or for people in general, and found that a lot of these patients are getting a really expensive test because doctors read somewhere in a journal article somewhere that it was actually useful for diagnosing whatever it was. But it turns out if you're giving someone the MRI already, you pretty much know that they have that disease. So you don't need to give it to them. So, and I don't remember what the exact test was, but it was something where Medicare and Medicaid started saying, no, we are not going to pay for this procedure. It's useless. And one of the weird things was, and this was something that we actually analyzed, or data that we actually analyzed in one of my classes on campus many years ago. People that got that extra procedure during surgery actually had worse outcomes. So it's, let's pay $30,000 to make you sicker. Really? Is that what we want? Well, what was going on? Spurious correlations. There is nothing we can do other than be like, say, a math god uh, to get rid of all of these different spurious correlations that we're going to be dealing with. The best we can do is try to eliminate them, try to make best guesses based on information that's up or that we have. In your 301 class, did anyone remember talking about something called Bayes' theorem or Bayesian analysis? Okay. So what we're going to be doing is going to be similar to Bayes' analysis. Um, but if you talk with the professor that teaches uh, the data science class and you talk with him about the Bayes analysis we did, he's going to look at you funny and go, wait, what? No, that's not how this works. So, couple things that are we're going to be doing this every Thursday, basically from here on out. You're going to get a data set that you're going to be analyzing. What you need to do with that data set is something called uh, partition it. What we're going to end up doing is breaking the total data set into two different groups, say 70% and 30%. 70% of the data is going to be called training. So if you have 10,000 rows of data, 7,000 rows of data are going to go in and create this regression model that we're doing, whether it's a multiple linear regression, logistic regression, forecasting regressions. I could not care less about that. Actually, with forecasting, we still have to worry about this or do this a little bit differently, but I'll break it down. 70% of the data goes into creating the model. 30% of the data is going to be used as, say, new data, data that the model has not seen, and we're going to try to use the model that we just made to predict the data points that we have over here. One of the things that can happen if we just take all the data, do our analysis the way that we're supposed to, and then at the end of it, report back what we have. We can do something called overfit the data, which means we have too many variables, which more than likely means we have lots of spurious correlations. That should be so lots of spurious correlations in there. And again, with these spurious correlations, depending on what they are, they could send you, or it could be showing that, hey, this really expensive test that has no impact on the outcome looks like it's doing a really good job predicting the outcome. So we want to get rid of as many variables as possible so that we're not overfitting. By breaking our data down into training and testing like this, we help to avoid some of the overfitting of the data. So part of what we're doing is we create a model and then we automatically test it. So the predictions that I had you make, what was it, 2 Thursdays ago? That's basically what's going to go on here. The difference is it's done automatically. So you don't have to sit there and put every single data point back into the model. It's automatic, and we see what we get. So once we're done with the partitioning, we can then create our model and look at our results. If you take the data science class, if you get into artificial intelligence or anything like that, when you're at this point here, so this is actually, again, part of a data prep. In order to, in general, in order to create these two data sets, you select something called a random seed. For a particular random seed, what ends up happening is, say you'll have the 7,000 data or rows over here, 3,000 rows of data over here. They will be quote unquote randomly selected. The truth is it's not randomly selected. They are part of a computer algorithm, and they're part of a recursive computer algorithm. Does everyone know what a recursive means in this? So you have a function, let's say you put in the number 2, and then it tells you that the answer is 4. That's going to be one of your data points that, say, goes into training. You now put 4 into the function and it gives you, say, 9. You pull out 9, or data point 9, put it into a certain group. You put 9 into the function, it gives you 6. You now have pull out the 6 and all that. The random seed is basically a starting point. When you look at a lot of machine learning, artificial intelligence, data science, textbooks and all that, they will actually set the random seed to a certain value. The reason they do that is because every time you use that same random seed, you're going to get the same results over and over and over. A lot of times the random seed that they select is actually going to be 42. Uh, Anybody know what's important about the number 42? Anyone? Yeah. If as a baseball fan, yeah, that's my 42. Anyone read Hitchhiker's Guide to the Galaxy? 42 is the answer to everything. So literally every time you go in and you start reading blog posts and you see random seed equals 42, it's because someone somewhere at some point read Hitchhiker's Guide to the Galaxy, thought it'd be a cool joke to say, hey, random seed is 42 because that's the answer to everything. What I'm going to have all of you do, though, is for your random seeds, you can use any number you want. You just can't use 42. And if you want to use, like, say, the last 4 digits of your phone, cell phone number, last 4 digits of your grandma's phone number, something like that as your random seed, I'm totally fine with that. But what ends up happening is with these random seeds, every new number we put in randomly assigns some of these rows to either the training column or the testing column, which means even though we're using the exact same data set, every single one of us is going to find that there are small changes in what variables are statistically significant. Some of these will be look like they are highly significant. Some of these will look like they're like a p-value. If it's below 0.05, we say it's statistically significant a lot of the time. So we might get 0.0499. So it'll be statistically significant, but not very. And essentially everyone's answers are going to be different based upon the random seed that you use. So what we're going to end up doing is once you've all analyzed the data, if since we're going to be using logistic and linear regressions in here, going to have all of you literally come up to the board and you're going to write down what is your random seed and looking at p-values. If Minitab says it's 0.0000, you're going to go and write all the terms that are in there. If it's between, say, 0.000 and what are all the terms you found in there, and then say 0.01 to 0.05, what terms did you find in there? And depending upon the data, we all might agree that, say, some of these variables are important. There's a chance that none of us will completely agree with what variables are statistically significant or important depending on what software we're using, which means every single one of you will have different results. And we're going to try to come up with a way how we can take each one of the models that you made, manipulate or try to come up with what are the variables that we should actually be looking at, trying to try to determine, are there some variables that what variables look like they could be spurious correlations, what variables might, like, say, show up in 30% of your models. So we could think of that as being important or statistically significant, but not very. Whereas if something shows up in 80 to 100% of your models, we can say those variables are actually statistically significant. And with these random seeds, like I said, they are a starting point. You put the number into the recursive algorithm, it just starts spitting out numbers, and those numbers get translated into, say, which row is going to go for training, which one's going to go for testing, and that sort of stuff. And when we're done with it, we're going to have a discussion. One of the things that if you were to take a class in linear regression from, say, the stats department, you take the entire data set, you analyze the entire data set the way that they teach you to, and then you report back these statistically significant variables. What is the model? Here's how we use the model. And that what we should be thinking is that that is basically an opinion. It's not a fact. It's all these models are basically an opinion. It might be a well-educated opinion, but just because, say, one of your professors said so at some point, how many of you have actually found out later that something a professor said kind of wasn't exactly true? Anyone? Anyone would admit that? So just because it's a educated opinion does not mean it's actually 100% correct. Oh, and this should be, sorry about that. Uh, so we're going to look at this. We're going to look at all the different opinions. And uh, I believe there's supposed to be like a journal article or something you're all supposed to be doing. Uh, Essentially, I have to write it down, but just to get you thinking about it. What I want you to do for that is actually going to be highly related to what we're doing here and what we're going to be doing the rest of the semester. But it's basically look up some different journal articles in whatever area of specialization you are interested in. So if you're finance, say AI in finance, if you're interested in accounting and stuff like that, how well do some of these AI systems and machine learning systems and software do? Yeah, if you're talking about marketing, how reproducible are the results you get from marketing based on what happens when, say, AI does these analyses? And we're going to look at reproducibility of results. Okay. Because if you do like a quick Google search, how reproducible is AI, even if you're interested in, like, say, you've got grandparents that are going through a lot of testing at a hospital. Uh, if you want to check out the use of AI for medical diagnoses, go for it. And just something to think about. Does everybody know who IBM is? IBM had their Watson computers. They were trying to sell Watson as an AI platform for helping diagnose patients. How well did that work out for them? You can look that up and see what's actually going on with that. But anyway, so just to give us an idea of what we're going to be doing next week, and you don't have to do any of this, but essentially what we're going to be doing once you get into Minitab, we're gonna go over this on Thursday, so don't start freaking out and trying to write all this stuff down. But when you get to regression, then fit the regression model. This thing down here where it says validation, we're going to be validating our models. And by using the validation thing here, uh, we're actually going to be doing that 70-30 uh, or training testing split. Let some of these stepwise regression methods that are in here run through, and then we're going to see what did you all find. So if you're going to try doing this in Python, it's a little bit more involved than this. But if you've already written out the script, you can just reuse the script over and over and over and over and over again, which is nice. But for right now, that's all that I've got. We will do the statistical analyses on Thursday. We'll have the data set, depending on how quickly we get everything done. We might actually do two different versions of this and then have a discussion about the different results that we got and why we got those different results. All right.